We spend billions of dollars accelerating protons to nearly the speed of light, smashing them together to observe the debris. The goal is to sort the wreckage into the standard model of particle physics. On the classroom poster, reality occupies 17 boxes, 12 matter particles, 4 force carriers, and 1 Higgs boson. Experiments at the Large Hadron Collider have empirically verified these pieces. We have the physical evidence and mathematical equations to describe how they fit together. Logically, because we can both observe and describe these building blocks, we should be able to simply count them. Cambridge physicist David Tong suggests that when we tally nature's fundamental constituents, the count stops being an integer. To perform a true cosmic census, we have to move past the classroom poster and look at what happens to these categories at the edge of quantum mechanics. The first complication comes from special relativity. To satisfy the math, every matter field supports both a particle and an identical antiparticle mirror with an opposite electric charge. These antiparticles play a distinct role in reality. Because they annihilate normal matter on contact and cannot transform into their twins, they require their own place in the census. Including these mirrors and oppositely charged W bosons, the tally reaches 30. The strong force adds 8 distinct color blends of gluons, making 37. Quarks also possess red, green, and blue color charges, plus anticolors, creating 36 distinct variations. The count is 61. In the quantum world, zooming in for a closer look causes our categories to splinter into a multitude of specific states. This splintering continues with chirality, where matter and force particles possess left-handed and right-handed states. Chirality dictates how forces interact with matter. The weak force, for example, only affects left-handed particles. Tallying every specific chiral and polarization state causes the census to explode to 118 distinct particle states. Every time physicists apply a strict definition to what makes a particle unique, the concept of a solitary building block fractures further. At this extreme level of categorization, the word particle fails to describe the underlying reality. Physicists instead count degrees of freedom, a mathematical metric for every independent way a quantum field can vary. To find the maximum number of degrees of freedom, we have to look at the high-energy environment of the Big Bang. At these extreme energies, field variations are no longer independent. Because the behavior of one field can be linked to the state of another, their mathematical values become fractional and codependent. This codependency results in specific values popping out of the math. Scalar fields hold 1 degree of freedom, force fields hold 62, and matter fields require exactly 5.5. By totaling these codependent values across the entire standard model, physicists Schwimmer and Komargatsky reached a final calculation of 995.5 degrees of freedom. While we have no idea why nature selected these specific values, they reveal a universe that refuses to be categorized by simple whole integers. If the universe contains nearly 1,000 degrees of freedom, we have to ask why so few of them are visible to us today. The answer lies in the A theorem, a rule proving that as the universe expands and cools, the number of effective degrees of freedom must strictly decrease. At the lowest possible energy scales, the math drops until only one particle remains, the massless photon. Depending on the energy of your perspective, the universe is built of 995.5 fundamental pieces, or just one. Our desire to count these pieces is a human impulse to force a static inventory onto a fluid reality. The census shows that the universe functions as a vibrating web of quantum fields, where the particles we see are simply ripples that change depending on the energy of the environment.